Okay, so we had technical issues in class and this was not recorded, the audio was not captured. So we're going to go through this very quickly, but so this will be an interpretation of the three items we've covered so far in SPSS, not fully, but partially. This will be referring to exercise 1. This is one of the graphics you were able to generate in exercise 1. And this is referring to this output here and this one here, independent t-test and dependent t-test or pair t-test, right? That you've already completed and you've uploaded in exercise 2. Okay, so this video is meant to just give interpretations to all this. And very quickly on my MATLAB, just to go through in case you're falling behind, there are 2 exercises so far, and the third one will be posted today for you to complete, so in SPSS. So the first exercise, exercise 1, is attached to the first video here. Okay, so if you watch this first video, follow through with the instruction on exercise 1 to complete 10.1 descriptive. So I will make this available for you to use late pass. I understand that some of you had problem with technology as well. Okay, and then exercise 2 is SPSS exercise 2 here. To know how to execute this, you need to have watched the second and the third video on independent and dependent t-test. Okay, and after watching this video, using the instruction exercise 2, you will be able to complete the homework assignment for exercise 2 over here. And it's just uploading the output for your data. And that output will look like what I'm going to be explaining today. So for exercise 3, which will be posted later today, you will be implementing what you've learned from completing exercise 2 and what you've learned from video for exercise 2, which I will be posting also later today. Okay, so let's go over to the worksheets or the outputs and try to interpret them. Okay, so this is one of the outputs you had from exercise 1, and it's a box plot or a side-by-side box plot comparing the distribution of the data for females and males. Okay, and so in chapter 1 we learned about box plots, and we covered a little bit of this in chapter 2, right? So I'm going to draw a histogram over this very quickly. So here, this, if you draw a histogram on this, will likely look this way. Not necessarily, but places to be close to that, right? And if you draw one on this, on male, it may look like this. Okay, so what we notice is that there are components of these box plots that indicate there are outliers on both ends, right? But that of female is much more skewed. Okay, so in summary, how do you interpret this if you're doing a research? Because when you're going to conduct a research, this is the first thing you do. You do a descriptive statistic, just see the shape and visualize how the data look. So you interpret this using in three ways, right? Excuse me. Yeah, you interpret this in 3 ways, essentially. What is going on here? Just a moment. Plug this back in. See why it's skipping. Okay, that is better now. So we interpret this in 3 ways. You interpret it based on measures of center. Okay, and I think I should write them here so I have more space. Based on measures of center, and for measures of center, you could use the mean, you could use the median, and you could use the mode. Any of this gives you idea of center. Okay, you may have seen that in the question for exercise 1. And then you can interpret this box plot based on spread. Okay, for spread, you will normally use variance, or we use standard deviation. Okay. And a third way to interpret this box plot will be based on shape. You write it over here. For shape, you essentially talk about skewness. Skewness. I don't think that spelling is correct. I'll cross-check it in a moment. Okay, so you essentially talk about skewness. I don't think this is there. Okay, so these are the three things you use the way you describe a box plot. Okay, so let's focus on this particular box plot, the one we have here, and try to describe them based on these three properties. Okay, so first you want to note that this here, this thick line in the middle here, and I think I should use a different color. Let me use black. So first you want to note that this thick line here, right, this thick horizontal line in the middle here represent the median. If you remember from class, the median will be 50th percentile. Okay, and here at the bottom here is your minimum. And at the end of the whisker here is your maximum. Okay. And then this point, of course, let me draw it on this on the plot for male. This point here, that line is the 75th percentile. And this point here, this line ending here is the 25th percentile. So you remember in chapter 2, we learned the 5-number summary, and that is what is represented by the box plot. But in addition to what we learned on the 5-number summary, there is this section marked in green here, okay, which are also here representing data that are outliers, right? And outliers are definitely data that are too far away from every other data, and they kind of skews the data, the distribution. So we can see here that the outliers for females skewed the data to the right. There is a little skew for the distribution for male, but not so much, so we can assume this is approximately normal. But for female, there is definitely a clear skew to the right. Okay, so how do you interpret this shape based on these three properties that we mentioned earlier here? So let's start with the center. So we're interpreting them comparatively, like we're interpreting the two side by side. Okay? So if we start with center, and maybe we should use black. Okay. If we start with center, here we have the median. So we could say that the median here we can just use the word the average. BMI. Okay, so average is used in loose term here. Average referring to all the measures of center, which include the mean, the median, or the mode. Okay, the average BMI for male and female about the same. Okay, they are more or less the same. Although somebody, if you're looking critically, you could say that the BMI for female is slightly higher than male. Okay, but we take approximate kind of outlook when we are doing this interpretation. Okay, so if you say that the median or the average BMI or the median BMI for females is slightly higher than male, you are also correct. Okay, but this is rough approximation. And in terms of spread, we could say that the distribution of BMI for female is more widely spread, right? It's more spread out than that of male. The distribution of BMI for females is more spread out than that of males. Okay, but to be more precise, a more precise language would be to talk about variance, right? There is a bigger variance. Female has the distribution of data sets for BMI for female has greater variance compared to the males, okay? So in place of the word spread, you can use variance. That is more appropriate technical term for that. Okay, so the last one, of course, is the shape. So we see that why the shape for the distribution of data for male is approximately normal. There's some skew here, but it's approximately normal. We see clearly that the distribution for the shape for BMI for female is skewed to the right, okay? So we're gonna make that comment. The distribution of BMI for females is skewed to the right. Okay, so that is a simple way to interpret your graph. So again, when you are doing data analysis, the first thing you do is descriptive statistics. And out of all the descriptive statistics, box plot is a common one. There's also histogram, right? And there could be pie chart or bar chart. But we've just explained how to interpret that, right? After you've conducted your analysis. This is a simple interpretation for. Okay, I think that is not working. Let me delete that and simply register fresh. Okay, so this is spread. Sorry, shape. Okay, so I hope that helps. And you can word this, put it in your own word. These are just rough explanation of what we are saying based on the graph, okay? And then we switch over to exercise 2. And from exercise 2, we did independent t-test, and we also conducted dependent t-test. So I expect you to watch the video there, use the appropriate data using the appropriate instruction here, use the instruction on exercise 2, watch these 2 videos. I will expect you to be able to generate these values I have here and then upload them in my MATLAB at the appropriate place. That will be uploaded in exercise 2, okay? But this is the interpretation of that output, okay? And you will be doing similar thing in exercise 3. So very quickly, the first part of the output is your group statistics, right? The group statistics. So the group statistics simply tells you the mean, median, standard deviation and standard error, as you could see. If you have formatted your data properly, this should read female, right? And this is male. Okay, so if you completed exercise 1 properly, that is what this should read. So we know 0 here represents female and 1 represents male. And these are their basic statistics: sample size, mean, standard deviation, and standard error. But we're focusing today on the second part, second output, which is the independent sample t-test, okay? So first, I want us to know that there are 2 parts to this table. I'm going to use the red to mark the first part. The first part is the Levene's test, of equality of variance, okay? And then the second part, and I will use green to mark that, the second part is the actual independent sample t-test, okay? All right, so let's start with the first part first. So for the first part, the Levene's test of equality of variance, the Levene test is simply trying to say, are these two groups spread out in a way that makes them still comparable, okay? The data set used here is just the height, right? For male and female, that is what is being compared, okay? But over here, this is BMI that is being compared, okay? But if I'm using this to illustrate that question, for example, Levene test will be questioning whether the spread here is too big that it makes the BMI for female not exactly comparable to BMI for males, okay? So over here, that is what the Levene's test is trying to ask, is the variances, are they spread out for both samples in a way that you can still properly compare them, okay? Now, if we look at this, a proper test, a formal test is conducted, and that test is the Levene's test, okay? The hypothesis test for Levene's test is written this way. So for everything for Levene, we're going to be using red. H naught. Levene's test, null hypothesis states that the variances are equal, right? So the variance of sample one for female, height of female, and height of male are equal. And symbolically, it's represented this way. Remember, this is population variance symbol, right? Sigma square for group one, you can say for female, is equal to sigma square for group two, you can say for male. Okay, so the variance of their heights are equal. That is what the null hypothesis for Levene's test states. The alternative hypothesis for Levene's test, we state that the variances are not equal. Okay, so symbolically, this would be written as H1 is such that the variance of female are not equal, or is not equal to the variance for male. Okay, and let me clean that last item there just to make sure. Oh, okay, let's see if we can actually just clean it as an event. Okay, just to make sure it's clean. So I'm using M and F to represent the variances, okay, for group one and group two. You can actually use any other thing, but the Levene's test is simply saying the two groups have equal variance. That is the null hypothesis, and the alternative hypothesis is saying the variances of the two groups are not equal, okay? So using the output, you can actually complete this test and arrive at a conclusion, okay? So I've mentioned this in class before, but remember that SPSS writes your p-value as significance, uses SIG or significance to denote p-value. So over here on Levene's test, there's not enough space, so it's used the abbreviation SIG to denote the p-value. And over here on the t-test component, independent t-test, it uses the full word significance. But in both cases, significance or SIG represents the p-value output for SPSS. Okay? So if we are looking at the component of the Levene's test, we see that the p-value, all right, for Levene's test, now remember Levene's test tests the quality of variance, tests the quality of variances when you have two samples. Okay, so Levene's test here is telling us that from what we can see, that we see that the p-value here excuse me, okay, the p-value, which is equal to 0.929, we see that this is actually greater than alpha. Alpha is not given to, we didn't talk about alpha when we're conducting this test, but it's taken for granted that whenever at the default setting for SPSS and most softwares, alpha is 0.05, except you change it otherwise. Okay, so we have alpha to be 0.0. So the Levene test p-value is indicating here that the p-value we have is bigger than the alpha value. And remember what we do when that is the case. So whenever p-value is greater than alpha, you recall that we reject the null hypothesis. Sorry, whenever p-value is greater than alpha, we fail to reject the null hypothesis. We fail to reject H0, okay? And the opposite is true. If p-value is smaller than alpha, we reject H0. I can write that down just for clarity. And let's use a different color to do that. Maybe purple. But if p-value is less than alpha, we usually reject H0. Okay, but in this scenario where we are looking at today on Levene's test, we see that the p-value for the Levene's test from this output is indicating a value bigger than alpha, where alpha is 0.05 for us. So the outcome of the Levene's test here is that we failed to reject H0, okay? And what is H0? H0 is saying the variances are equal. That's what H0 is saying. So if you fail to reject H0, it means you are going to assume in your test that the variances are equal. But if you reject H0, assuming the p-value here was smaller than 0.05, then we would have assumed the variances not to be equal. What difference does this make? It tells you which line of test to interpret, either this or this, right? So you see here, if we assume equal variances based on this test, then we need to interpret the first line. But assuming the p-value here was significant, assuming one of the data sets was spread out more than the other one, then we are going to assume that the variances are not equal. And the formula had been adjusted to give you a different output. Okay, so when we're calculating by hand in class, we calculated the first one. We just ignored the second one because it's a little bit more complicated. All right, so on this question, on this output, for example, during your assessment, your finals, I could give you this output and ask you to determine whether the variances are equal or not. So based on the output, you want to focus on the Levene's p-value. If the p-value is greater than 0.05, then you're going to fail to reject H0. And if you fail to reject H0, H0 is saying the variances are equal. So if you fail to reject it, then you are assuming they are equal. And that means the result you will interpret is the first one, okay? But if you reject H0, it means the variances are not equal. And if the variances are not equal, then the result you interpret will be the second one, the second row, okay? So for this scenario, we are using to illustrate this, the result we are going to interpret is the first one because the variances are shown to be equal because we rejected H0. I mean, because we failed to reject H0. Okay. So how do we interpret this? There will be question on exercise 3 to make you answer questions on variances the way I just explained it here. But how do we interpret the t-test results on the right-hand side? Okay. So on the right-hand side, there are just few things you need to pay attention to, and the rest, are things you've come across before, or yeah, I think they are all things you've come across before. So first thing to pay attention to is your test statistic, right? And then next you have your degree of freedom. And then you have your p-values. Okay, so in this independent t-test, so if you remember how we computed the degree of freedom, we added the two sample size and we subtracted 2. So if you come over here, this is 147 plus 153, that will give you 300. If you subtract 2, you get 298. That is how you got the degree of freedom here, okay? And then you have your p-value. So SPSS gives you 1 tail test and 2 tail tests automatically. So you choose the one that you that applies to what you're testing, okay? So for this right-hand side, the independent sample t-test, let's go ahead and interpret the result we have here. I'm going to copy it, I think. Let me see if I can copy it and paste on the next page. That way we don't have to go forth and back. Okay, that worked. Okay, so looking at the results on the page here, I can move that up a little bit. How do we interpret the right-hand side, the one on green? So let's switch to green here. Okay, I'm missing my pen again. Okay. Bear with me. This is failing to function. My waiting for it stopped working. Okay, I think it has picked up. So we look at the green component to interpret the t-test. So how do we interpret that? If you look at the p-value and we take it that we are doing 2 tail tests, if you look at the p-value, it's smaller than 0.5. In fact, it's so small that SPSS decided to put in less than 0.001 here as the output, okay? So how do we interpret the results? First, understand that you're doing independent t-tests and that we are trying to test the equivalence or otherwise of the heights for male and female. So this t-test is asking, is the average height for male and female, are they equal or different from each other? Okay. So let's take the null hypothesis first for clarity. So the null hypothesis here is saying the average height for male or female first is equal to the average height for male. Okay. And then if this is your null hypothesis, then the alternative hypothesis, of course, will be that the average height for female is not equal to the average height for male. So this is the test we are conducting using this table, okay? And when this was conducted, we found out the test statistics to be negative 14.771, the degree of freedom to be 298, and the p-value to be much smaller than 0.05. It is smaller than 0.001. That is what the SPS is showing us. So how do we make conclusion here? How do we state our conclusion? You could write this in different ways, but I would say since the p-value which is smaller than 0.001, since this value is actually less than is less than alpha, which is equal to 0.05, we reject the null hypothesis. Okay, reject the null hypothesis. And when we reject the null hypothesis, what do we conclude? The null hypothesis says that the average height for male is equal to the average height for female. Okay, now we rejected that. So we're going to conclude in favor of the alternative. So we conclude by saying there is evidence, sufficient evidence. So let's write that very well. There is evidence in the data to suggest that the average height, or you can say the mean height, for males or for females differs from the average height for males, or for the mean height for males. Okay, so this is just one way of stating that. You can say it in your own words, however that appeals to you. But key things, I mean, the key thing should be captured. The key thing is that we are rejecting the null hypothesis and we are supporting the alternative. And the alternative says they are not the same, they differ. So that is what we stated here. But what is different from what we did when we were in class is that we are adding more evidence to this, right? So when you state this, you are expected to put in a summary of your evidence, and it is written this way. The t-test statistics, in parentheses, your degree of freedom to 98 is equal to negative 14.771. That's our test statistics. Okay, so first of all, you write it that way, right? You write your T parentheses, this is a subscript really, right? T parentheses 298, 298 is your degree of freedom, right? Is equal to the value of your test statistics, comma, p-value. So our p-value is less than 0.001, parentheses close. Okay, so this is how to report your results using the output we've gotten for SPSS. Okay, this is exactly the same thing we do also when you have a paired sample t-test. Okay, but notice that for paired sample t-test, there is no Levene's test. There is no Levene's test because the sample, this is a paired sample. The two samples have the same sample size. And if they have the same sample size, the impact of the differences in the variance are usually not, it's usually not significant. Okay, so kind of ignore Levene's test for this case. Some people do conduct some kind of tests, but it's somehow generally approximately not really needed. So we ignore Levene's test and we go ahead to interpret the attribute for paired sample t. Okay. The interpretation is exactly the same. Exactly the same. So over here, again, you see we don't have Levene's test, which was on the left. We just have the paired sample t test. So in other words, if you look at this shape, we don't have the red part. We just have only the green part for the paired sample t-test. Again, the reason is that the sample size are equal because you're dealing with a pair. And when the sample size are equal, the effect of differences in variance doesn't matter much. Okay, so how do we interpret this? Look at your test statistics over here, right? And this is your degree of freedom. And these are your p-values for two tail and one tail, okay? And you could use the one that applies to the research you are doing. Okay, so the interpretation is the same thing, right? So we quickly write as a practice, since the p-value this time again, whether you're doing two tail or one tail, which is less than 0.01, is smaller than alpha. Again, alpha was not given, but we take the default, which is 0.05. Again, we reject H0. We can write it in full. We reject the null hypothesis. And what is the null hypothesis here? Let me write it in red. Remember, we're dealing with pair sample. we did say that the null hypothesis is that mu d is less than 0. Okay, but before we get to that point, if we expand that, so this is saying the difference in mean is smaller than 0. Okay, and the alternative is saying the difference in mean is not smaller than 0. Okay, and oh, sorry. So what we're doing is 2 pair here, not 1 pair. Okay, let me correct that very quickly. So we're saying here the difference in mean is equal to 0 for 2 tail. Okay, and then the alternative is that the difference in mean is not equal to 0. Okay, so I was going to explain that the first line could be expanded further. So you could write it as H naught is the mean of group 1 is equal to the mean of group 2. Okay, now if these two are truly equal, you will find out that a simple way to write it will be also that H naught is that mu of group 1 minus mu of group 2 is equal to 0, right? That will happen if they are truly equal. The mean of the first group and the second group will be equal to 0. Let me write this. Okay, I see it came inside this shape, so it's affecting the write-up. So let me put it somewhere that it will come out more clearly. Okay, so what we are saying is that if H naught is that group 1 and group 2 are equal for a paired sample, then it will mean that another way of writing that could be that H naught mu1 minus mu2 will be equal to 0, right? So because if they are equal, if you subtract them, you should get 0. And that is, if you replace this with mu d, which says difference of 2 mean, if you replace this with this symbol, then you see that that is how we got this written this way. Okay, so they are technically the same thing. And the alternative is that they're not equal to 0. Okay, so let's go back to green and finish up our interpretation. So we see that the test statistics is the p-value is less than alpha. If they are less than alpha, then we're going to reject the null hypothesis. And the null hypothesis is saying that the difference between the two data is 0, or that the two data, the mean of the two data are equal, right? So that's one way of saying it. It's either they're equal or you're saying the difference between their mean is 0, which is what we represented here. Okay, so now we rejected H naught. We rejected that the difference is equal to 0, or we rejected that they are equal. We are going to support the alternative. So we're going to say here, there is evidence in the data to suggest that, and I'm using the word suggest, right? Because if you take another sample, you might get something different, okay? But overall, on average, the result is supposed to be consistent. There is evidence in the data to suggest that the mean weight. So if you read the instruction for this question, we are comparing the mean weight for twin 1 and twin 2, for two identical twins. Okay, so I'm going to phrase the conclusion in that context. So there is evidence in the data to suggest that the mean weight for the identical twins differs. Okay, so and just like before, you're going to put the summary of that evidence, and you do it the same way. Your T parenthesis, your degree of freedom, which is 146 in this case, is equal to your test statistics, which is minus 3.367, right? Comma, then you add your p-value. So again, here we have p-value less than 0.001. Okay. If you have an actual number here as your p-value, you just say p-value equal to that number. Okay. But SPSS is telling us that it's so small that it's smaller than 0.01. So we just put it over there because we don't know the exact number. It was not given to us. Okay. So that is how to interpret paired sample t-test. You see that it says same exact interpretation as independent sample t-test. Okay. But if you have followed the exercise and you were able to generate these two videos, these two table for independent and dependent t-test, then what I have presented here is the just the interpretation, right? So again, if you go to the website, these two videos here tells you how to do that. And then if you follow this exercise, you're going to generate the table I'm interpreting right now. And what you're expected to do in exercise 2 is just to generate those two tables and upload them here. Okay. Exercise 3, we test you your understanding of the interpretation I've just given right now here. Okay. So I hope that helps. And just to round off, there are other things on the table I didn't mention, but there are things that you're familiar with. For example, you have the confidence interval here, the lower and the upper tail confidence interval. Okay. You have the mean, standard deviation, standard error. We are used to calculating all these things before now, right? So over here, again, you also on the independent sample t-test, you also have the confidence interval, right? So if you check the formula that we use to compute the test statistics, if you apply that formula using your standard error here, if you do standard error here and the difference in mean here, you get your test statistic, right? So if you divide negative 12.4378 by 0.8420, you are going to get the test statistics. So if you do difference in mean divided by standard error, you get your test statistics. Okay, we walk through this by hand. My focus here is that you're able to state this test and state your conclusion using the information you have on this table. And you should be able to do so for independent t-test and do the same thing for paired or dependent t-test. Okay, we'll stop here.